Good morning, ladies and gentlemen. Welcome to the SAIEE Rotating Machine Section webinar on analysis of different winding configurations. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on your device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel. The QR code on the bottom left of your screen is which you can scan and register for this subscription, this YouTube channel. It is free. You'll also find ±300 webinars listed in various playlists in this channel, but the recording of this webinar will be listed under the Rotating Machine Section playlist. A certificate of attendance will be issued a few days after this webinar. I'd like to introduce you now to our host today, Mr. Fani Steyn, who's the chairperson of the SAIEE Rotating Machine Section, and he currently serves as the LV and HV executive for the Electric Motor Division of WEG Africa, situated in South Africa. In this role, Fani oversees the WEG motor business, encompassing proposals, geared motors, technical support, and project departments. Fani effectively manages a dynamic WEG team, consistently achieving outstanding results. Over to you, Fani.
Thank you very much, Minx, and good morning and welcome to everybody joining us online. It is our great pleasure today to host the technical forum here. And if you can just go to the next slide, please. I want to introduce to you today Mr. Hilary Idoko. He is the Best Paper Award winner at the SALPEC 2025, and we have the honor of having him here at the SAIEE. And in this webinar, Mr. Hilary Idoko is a doctoral student in the Department of Electrical Engineering at Tshwane University of Technology in Pretoria, South Africa. He obtained a BA Engineering in Electrical Engineering and an M Mechanical Engineering in Electrical Machines and Drives from the University of Nigeria, Nsukka, in 2012 and 2016 respectively. He is a member of the Nigerian Society of Engineers and a registered member of the Council for Regulation of Engineering in Nigeria. His research interests include electrical machines and drives, power electronics, and renewable energy technologies. He has published research papers in both national and international journals and conferences. We welcome you here today, Hilary, and we're looking forward to all the knowledge that you can share with us today. Let's keep to the questions to the end. Let's not have discussions during the presentation, and then we'll also have a look at the questions on the chat when we finish the presentation. So thank you so much to everybody, and welcome here. Thank you. Welcome, Hilary.
Thank you. My name is Hilary Idoko. I'm a doctoral student at CUT. And the title of my presentation is Analysis of Different Winding Configurations of Double-Stator One-Feed Flux Switching Motor. Go to the next slide. My presentation outline is Introduction, Study Objectives, Proposed Machine Topology and Methods, Winding Configurations, Results, and Conclusion. Next slide. Introduction. Concerns on global warming has always been the motivation towards researches on electrification of transportation sector. This is because transportation sector contribute a very significant amount of carbon emission. And the key component in this electrification is traction motor, because traction motor affects other components of electrification, such as power electronics, control to be used, and also traction motor to some extent, to a great extent, determine the overall cost of electrification. And the most favored traction motor is permanent magnet motor because of its high efficiency and high torque density. But permanent magnet motor have some challenge of cost, and it cannot be used in a very harsh environment. That was led to search on finding no PM alternative. And among no PM alternative motors, one-speed flux switching motor is the most promising. This is because it compares favorably with permanent magnet motor, because the high torque density can be achieved without altering its structural envelope. So, but the challenge with one-speed flux switching motor is that when you want to design it for a high torque or for a heavy-duty application, it will have a very large split ratio, leading to poor utilization of space. Because of this challenge, in order to solve this challenge and also to increase torque density, double-stator one-piece flux switching motor is the answer. Although this double-stator one-piece flux switching motor has a lot of potential for application in different areas, the nature of this back-emf have not been studied or investigated. So, and what determines the nature of back-emf of double-stator one-piece flux switching motor and other motors is the type of winding configuration used. So, the main objectives of this, our research, is to analyze the nature of back-emf waveforms of double-stator one-piece flux switching motor for different winding configurations. Next slide. Proposed machine topology. The proposed machine topology we use in this research are shown in figure 1.1. This is a typical topology of double-stator one-piece flux switching motor. It has a double-stator, outer stator, and inner stator with a single rotor in between the two stators. And both the outer stator and the inner stator has feed windings and armature windings, as you can see in figure 1.1a. And in this research, we considered 4 different topologies. And these 4 different topologies, they are equal in size and the same rating. Figure 1a have the only difference between the 4 of them is the number of the rotor poles. Figure 1a has 10 rotor poles, B has 11 rotor poles, C has 13 rotor poles, and D has 14 rotor poles. All these 4 models will be modeled in 3D finite elements analysis and under different winding configuration, and the nature of their back-emf will be investigated and compared. And the relationship between electrical position and mechanical position in this motor is represented by equation 1.1 for generator-oriented perspective. And for the rotor-oriented perspective is equation 1.2. Next slide. Our research approach as follows: topology selection, core position determination by motor-oriented perspective, FEA modeling, result analysis, and comparison. Next slide. Winding configurations. Two most important or most popular winding configurations for Flux switching motor are all pole wound and alternate pole wound. And that's what we use in carrying out our research. For 10 rotor pole, the winding configuration for all pole wound are shown in figure 2A, while the phase coil vectors, which determine the physical position of the coil in this stator, both the outer and inner, are shown in figure 2B. And for the alternate pole wound winding configuration for 10 rotor pole is shown in figure C, while its coil vector, phase coil vector, are shown in figure 2D. And the resultant voltage equations for both all pole wound and alternate pole wound are shown. For the all pole wound, they are shown in equation 2, 3, and 4. While for the alternate pole wound is equation 5, 6, and 7. As you can see, the total voltage in outer stator is the addition of coil voltage 1, 2, 3, and 4. While for the inner is the same thing. So for the overall force voltage in this all pole one is the addition of outer phase voltage and the inner phase voltage. The same thing is applied to alternate pole one configuration. Next slide. For the 11 rotor pole, the YV configuration for all pole one is shown in the figure 3A, while its phase coil vector is also shown in figure 3B. While for the alternate pole ones, the winding configuration is shown in figure 3C, while its phase coil vector is shown in figure 3D. The resultant voltage, just like in 10 rotor pole, so the first voltage is the addition of the coil voltage. Next slide. Figure 4 is the winding configuration for 13 rotor pole. As you can see, something you can observe here is that 13 rotor pole and 11 rotor pole, they have similar winding configuration. The only difference is that the phase G coil in 11 rotor pole, for the 13 rotor pole, they will become phase C coils. So their first coil, B and C switch from when you move from 11 rotor pole to 13. Phase B coil switch to phase C phase coils. That's really different. So every other thing are the same, like 11 rotor pole. Next slide. So figure 5 is the winding configuration for 14 rotor poles. For all pole one is is shown in figure 5a, while its first coil vector is shown in figure 5b. As you can observe too, that 14 rotor pole have a similar winding configuration with that of 10 rotor pole. The only difference is that is the switching of first coil of B with C, where you move from 10 rotor pole to 14 rotor pole. Every other analysis is the same as that of 10 rotor pole. Next slide. Results. Figure 5 and figure 6. Figure 4 and figure 5 show the results of 10 rotor pole. Figure 4a is the nature of the back EMF of 10 rotor pole. As you can see, coil voltage for 10 rotor pole, coil voltage is unsymmetrical, but first voltage is symmetrical. It is not clear in the figure 4a, but when you look at table 1, that is the normalized harmonic content, you will see that coil voltage contain both even and odd harmonics, showing that it is unsymmetrical for both inner coil and outer coil. But when you sum the outer coil together, when you connect them in series and sum it, you will see that outer phase voltage will become symmetrical. Some of the harmonic will be eliminated. The same with the inner phase voltage. So, and when you sum the outer phase voltage together with the inner phase voltage, we see that the overall phase voltage, a lot of the harmonic will be eliminated, leaving only 7th order harmonics and 13th order harmonics. And also, as you can observe, that the coil voltage has a lot, the total harmonic distortion of coil voltage is very high, while that of phase voltage, the total harmonic distortion has been reduced to a great extent. As you see, for the outer coil voltage, the total harmonic distortion is 16.54%, 30.90%, while the inner is 16.54%. But for the first voltage, the overall phase voltage, the total harmonic distortion is 5.08%. Showing that, as you can see, that by the time you connect the coil voltage in series, some of the harmonics will be eliminated in double stator, 1 feet plus switching mode, 10 rotor poles. Next slide. Results of 11 rotor pole. Just like in 10 rotor pole, coil voltage is unsymmetrical, but the first voltage is symmetrical. But one thing to notice, to observe here, is that for the 11 rotor pole, the first voltage, the overall first voltage, contains 3rd order harmonics, 5th order harmonics, which is a problem. Total harmonic distortion is reduced just like in 10 rotor pole, but not to the extent of 10 rotor poles. Next slide. For the 13 rotor pole, the result of 13 rotor pole, as you can see, It have a similar result like 11 rotor pole. All of them, all the models, their core voltage is all symmetrical, as we can see due to the presence of both even and odd harmonics. But for their overall phase voltage, some of the harmonics have been eliminated. Just like 11 rotor pole, the phase voltage contains third order harmonics and fifth order harmonics. Next slide. For the 14 rotor pole, just like 10, 11, and 13, its core voltage is unsymmetrical, but phase voltage is symmetrical, as we can see from the table. We see that just like 10 rotor pole, because 14 rotor pole and 10 rotor pole, they have a similar results and a similar winding configuration. The only difference here is that, unlike in 10 rotor pole, where the phase voltage, the prominent harmonics there are 7th harmonic and 13th harmonic in 10 rotor pole. But in 14 rotor pole, we see that for the first voltage, overall phase voltage, the prominent harmonic there is 5th harmonics. But in 14 rotor poles, the total harmonic distortion is the least among all the 4 models. So, slide. So, in this place, slide 1, we compare the 4 models based on all pole 1 winding configuration. As you can see, for the 10 rotor pole, the prominent harmonics there are 7th harmonics and 13th harmonic. While the 11 rotor pole, the prominent harmonic there is third order harmonics, 5th and 7th. While for the 13 rotor pole, the prominent harmonic there is third order harmonic and 5th order harmonics. While for the 14 rotor pole, the prominent harmonic there is 5th order harmonics and 13th order harmonics. So if you compare the 4 models together, you see that in terms of total harmonic distortion, 14 rotor pole perform better, followed by 10 rotor pole. 11 rotor pole and 13 rotor pole, they have a higher harmonic distortion, and also they contain the 11 rotor pole and 13 rotor pole contain third order harmonics, 5th order harmonics, which is a problem. So if you have to choose between these 4 models, the best to choose is 10 rotor pole. Next slide. So here, the alternate pole 1 configuration, they behave the same or similar to that of pole 1 configuration. So the only difference is that the magnitudes of the harmonics will be reduced. So we did it, it was not repeated. We compared all pole 1 configuration here and alternate pole 1 configuration. As you can see, when you compare in each model, if you compare alternate pole 1 with all pole 1, we see that all pole 1 configuration performed better in each of the models. So, as you can see, if you look at the total harmonic distortion between all pole 1 and alternate pole 1 configuration in each model, you see that for the rotor pole model, while the alternate pole 1 configuration has a harmonic distortion of 2.55%, this all pole 1 configuration has 5.08%. For 11 is 16.58% against 11.24%. For 13 rotor pole is 16.35% against 10.56%. While for the 14 rotor pole is 12.79% against 3.64%. So in summary, between this comparison, it's better to use alternate pole 1 configuration in double-stator 1 feet plus DC motor instead of alternate pole 1 configuration. Next slide. In conclusion, the back-emf waveform of 10 rotor poles, 11 rotor poles, 13 rotor poles, and 14 rotor poles double-stator 1 feet plus switching motor with different winding configuration are investigated. It's shown that although called back-emf waveform are unsymmetrical, phase back-emf are symmetrical, except for 10 rotor pole and 14 rotor pole machine that are unsymmetrical for alternate pole 1s. Also, all pole 1 configurations have lower percentage of total harmonic distortion, which signifies lower operational noise. In this conclusion, there's something I didn't mention in the last slide. So, unlike all pole 1, whereby the overall phase voltage is symmetrical, for alternate pole 1, it's only 13 rotor poles and 11 rotor poles that have their overall voltage symmetrical. 10 rotor pole and 14 rotor pole, their overall voltage is unsymmetrical. The overall phase voltage is unsymmetrical for alternate pole 1s. Next slide. Okay, thank you for listening.
Well, thank you so much. We really appreciate that. Very interesting. I don't know if there's any questions in-house first before we go to the chat. I don't see any questions here. Here's the chat.
In the questions panel, Fani.
Okay. Don't know what happened there.
Can I help you out, Tiffany, and read the questions?
In the meantime, maybe I have a question. Yes, please.
Okay, can you just please mute when I ask the question so we don't have feedback for the online audience, please?
A moment.
Thank you. Our first question here is from Louis Cook. How does the harmonic spectrum H1 to H50 generated inside the machine affect the 1 cooling and 2 insulation design, 3 output torque, and 4 overall machine efficiency?
Pardon, repeat the question.
Can you please repeat?
How does the harmonic spectrum H1 to H50 generated inside the machine affect the cooling and insulation design, output torque, and overall machine efficiency?
Okay. Thank you. For one thing I want to note here is that for unlike conventional motor, whereby what is needed is the fundamental harmonics, every other harmonics is considered as a problem. So in a flux switching motor, not all the harmonics is a problem. There are some useful harmonics. So, but to answer his question, harmonics, you know that harmonics has a higher frequency, and AD current and hysteresis losses is a function of frequency. That means the higher the harmonics, the higher the core losses, which will affect the frequency. And it will hit the machine, to contribute in hitting the machine, which also will affect the insulation. But in this particular 1-speed flux switching motor, the target actually is not to eliminate all the harmonics. So because some harmonics are very useful in the torque production, only few harmonics like the third order harmonics, which increase the neutral current, and fifth order harmonics, which contribute counter electromotive force in a large machine, is the target to be eliminated. So what other harmonics may be useful when you analyze the torque production of it?
Thank you. We have our next question from Mr. Mark Gordon. He's asking, have you measured the vibrations or acoustic noise?
No. The noise. Yeah, what I said. I said we didn't consider noise or vibration in the analysis.
Let me ask a question here. Did you build the machine?
Yeah, we have built a prototype of the machine.
Okay.
So, although we encountered a challenge, and the challenge we encountered is that it's a double-stator, and rotor is in between the two stator. So we encountered the mechanical problem. We use in the prototype we designed, we used a single bearing. So because of that single bearing, we couldn't operate the machine at a rated value. But we are trying to find a solution to it, although we have already discovered a solution to it, so which we are working on now. We want to use a 2 bearing now so that we can run it at a rated.
Thank you. And then we just have a comment from Mehmood Hafaji that's saying, very insightful research. Thank you for the presentation. Fani, that's all the questions we have online. I don't know if you have any in the room.
Let's take a last question here. Let's see if anyone have a question inside. Thank you, Rian.
Because of the, if you see the shape of the machine, you have double stator, outer stator, and the inner stator, and the rotor in between the two stator. If you use if you use double stator, if you use double bearing, you see that you are going to encounter problem. How to take the connection from the inner stator out? Huh? No, we try to avoid the slip ring. That is one of the advantages of close switching motor. Eliminated one of the advantage close switching motor over all those conventional motors.
Thank you so much, Rian and Hilary. I think there's 2 windings, 2 stationary windings, and then there's a rotor between the 2 windings. For the prototype, they used 1 bearing so that they can reach the connection on the inner stator. But I'm sure as this technology evolves and we get 2 bearings, there'll be a methodology around how to connect to the inner stator. So yeah, very interesting. Thank you so much, Hilary. We appreciate your time coming here explaining this. I'm sure we'll have a few questions here, having some tea outside now as well, as people thinking about it. It was quite interesting. Yeah, so thank you so much. We appreciate it a lot. Thank you to everybody, Minx as well, for your assistance on the webinar, and Tando as well in-house here. We appreciate it. So thank you again to everyone joining here today. Have a good day.